Welcome to the New Chemist podcast. We're glad you're listening. Feel free to download this podcast on Spotify, Google Podcasts, and Apple Podcasts. Here on the New Chemist, we discuss chemistry, which simply put is the science of change, as well as the other sciences, careers, community, research, and COVID-19. Welcome to Lecture Cast, where we discuss general chemistry topics. This is a podcast lecture series on general chemistry. Today, we will be talking about chemical equilibria. My name is Mr. Ferguson. I am a adjunct faculty, and I'm also an associate member of the Royal Society of Biology and an associate member of the Royal Society of Chemistry. Hello and good evening, everyone. What a moment where everyone is on their feet holding a flag and supporting their concept. Team Equilibria on one side of the field and Connects on the other side of the field. Now let's get ready to rock and roll. These two experimenting concepts exemplify in the spirit of chemistry that skill displayed in different ways perhaps, but by world-class chemists again. There is history to be made or added, concepts to be learned, and skills to be gained. Just before we dive into the concepts, I want to remind everyone you are not alone. This is an academic community. Remember to get help when needed. Reach out to university services if needed. Never give up. Keep trying. We are here to help you be intelligent, ethical, and responsible scientists. But at the end of the day, you must be responsible, ethical, and hardworking. So let's talk about Le Chatelier's principle. When a system at equilibrium is disturbed by a change in the amount of a reactant or product, a change in volume, or a change in temperature, the system shifts in the direction that minimizes the disturbance. So a quick overview, we'll discuss the equilibrium constant. Remember the word extent. We'll talk about dynamic equilibria. Remember a treadmill. The equilibrium constant expression. Remember the law of mass action. The equilibrium constant. States of matter and the equilibrium constant. Calculating K. The reactant quotient. K and pressure, find the equilibrium concentrations, and the Chatelier's principle. These are just a few of the topics we will cover. In some of these topics we will cover today. The rest we may cover in later episodes. So the equilibrium constant. The relative concentrations of the reactants and the products at equilibrium are expressed by the equilibrium constant K. Let me say that again. The relative concentrations of the reactants and the products at equilibrium are expressed by the equilibrium constant K. One more time. The relative concentrations of the reactants and the products at equilibrium are expressed by the equilibrium constant K. The equilibrium constant. The equilibrium constant measures extent. How far a reaction proceeds towards products. How far a reaction proceeds towards a specific point. So a large K, much greater than 1, indicates a high concentration of products at equilibrium. A large K, much greater than 1, indicates a high concentration of products at equilibrium. The equilibrium constant measures extent. How far a reaction proceeds towards products. A small K less than 1 indicates a low concentration of products at equilibrium. Dynamic equilibrium. Most chemical reactions are reversible. They can proceed either with the forward or the reverse reaction. Depending on the type of reaction you're referring to, certain steps may be more or heavily weighted. When a chemical reaction is in dynamic equilibrium, the rate of the forward reaction equals the rate of the reverse reaction, so the net concentrations of the reactants and products do not change. When a chemical reaction is in dynamic equilibrium, the rate of the forward reaction equals the rate of the reverse reaction, so the net concentrations of the reactants and products do not change. One more time. When a chemical reaction is in dynamic equilibrium, the rate of the forward reaction equals the rate of the reverse reaction, so the net concentrations of the reactants and products do not change. So dynamic equilibrium. However, this does not imply that the concentrations of the reactants and the products are equal. So, the reaction being at equilibrium does not imply that their concentrations of the respective reactants and products in that reaction are equal. Now let's talk about the equilibrium constant expression. The equilibrium constant expression is given by the law of mass action and is equal to the concentrations of the products raised to their stoichiometric coefficients divided by the concentrations of the reactants raised to their stoichiometric coefficients. So when you look at the reaction, you see that there are numbers in front of those chemical symbols. Those are typically referred to as the stoichiometric coefficients. So when you write an equilibrium constant expression, you put the concentration of the reactant in brackets, in square brackets, and the exponent for that square bracket term is the stoichiometric coefficient, and it's products over reactants. So also, the equilibrium constant can be expressed in terms of concentrations or in terms of partial pressures. Remember the relationship between pressure and concentration within the context of moles? The two constants are related. Concentration must always be expressed in units of molarity for Kc. Partial pressures must always be expressed in units of atmospheres for Kp. The equilibrium states of matter and the equilibrium constant. The equilibrium constant expression contains only partial pressures or concentrations of reactants and products that exist as gases or solutes dissolved in solution. Pure liquids and solids are not included in the expression for the equilibrium constant. One more time, the equilibrium constant expression contains only partial pressures or concentrations of reactants and products that exist as gases or solutes dissolved in solution. Pure liquids and solids are not included in the expression for the equilibrium constant. So calculating K. We can calculate the equilibrium constant from equilibrium concentrations or partial pressures by substituting measured values into the expression for the equilibrium constant as obtained from the law of mass action. So what does this mean? We can calculate K given the concentrations or partial pressures when we have those measured values. As we progress in this discussion, we'll also in later episodes we'll introduce the idea of using ice tables in which you look at the initial change in equilibrium concentrations. You look at what you start off with, the change, which can be denoted by some x, some variable term, and then you net, or the net expression will be the initial minus the change, and you use those terms at the bottom. The E section of the table, use those terms, you form an expression using the law of mass action, and from that expression you equate it to the known equilibrium constant, and you solve for x, and you're able to obtain the different concentrations of the reagents at different points in the reaction in order for you to progress and solve the problem. So calculating K. In most cases, we can calculate the equilibrium concentrations of the reactants and products, and therefore the value of the equilibrium constant from the initial concentrations of the reactants and products and the equilibrium concentration of just one reactant or product. So one more time, in most cases we can calculate the equilibrium concentrations of the reactants and products, and therefore the value of the equilibrium constant from the initial concentrations of the reactants and products and the equilibrium concentration of just one reactant or product. Now, depending on whether the type of substance or reaction that you're referring to, that may be easier said or easier done. So you really have to know the reaction, understand the reaction that you're referring to. For example, with strong acids and strong bases, it's very easy or relatively easy when compared to weak acids and weak bases. So if say you have the equation is A plus B turns to C plus D, where the stoichiometric coefficient of A is little a, the stoichiometric coefficient of B is little b, the stoichiometric coefficient of C is little c, the stoichiometric coefficient of D is little d. That will be, if you're looking at the video that will be posted eventually, it will be capital C in brackets raised to lower c, capital D in brackets raised to little d over capital A in brackets raised to little a, and capital B in brackets raised to little b. And this is derived from the concept or the expression in which you denote terms that state or show that the forward rate is equal to the reverse rate. So the reaction quotient. The reaction quotient, Q, is the ratio of the concentration or partial pressures of the products raised to their stoichiometric coefficients to the concentration of the reactants raised to the stoichiometric coefficients. And the key thing to remember, the difference between Q and K is Q is at any point in the reaction. K is at equilibrium. So, it's important to know the reaction coefficient, the reaction quotient is at any point in the reaction. The equilibrium constant is at K. Yes, at K. The reaction quotient is the ratio of the concentration or partial pressures of the products raised to the stoichiometric coefficients to the concentrations of the reactants raised to the stoichiometric coefficients at any point in the reaction. The reaction quotient, like K, Q can be expressed in terms of concentrations or partial pressures. At equilibrium, Q is equal to K. Therefore, the direction in which a reaction proceeds can be determined by comparing Q to K. One more time. At equilibrium, Q is equal to K. Therefore, the direction in which a reaction proceeds can be determined by comparing Q to K. If Q is less than K, the reaction moves in the direction of the products. If Q is greater than K, the reaction moves in the reverse direction. If Q is less than K, the reaction moves in the direction of the products. If Q is greater than K, the reaction moves in the reverse direction. So finding equilibrium concentrations. There are two general types of problems in which K is given and one or more equilibrium concentrations can be found. For the first type, you have the equilibrium constant given and all but one equilibrium concentrations are given. We solve this type by rearranging the law of mass action and substituting the given values. For the second type, K and only initial concentrations are given. We solve the second type by creating an ice table and using a variable x to represent the change in concentration. And depending on our equilibrium constant, whether it is smaller than 10 to the minus 5, we can use the x as small approximation. When you do the x as small approximation, whatever you subtract x from, the ratio of those things when multiplied by 100 should be less than 5%. If that's not the case, the approximation won't be as sound. There are two general types of problems, again, in which K is given and one or more equilibrium concentrations can be found. First type, K and all but one equilibrium concentrations are given. We solve this type by rearranging the law of mass action and substituting the given values. Second type, K and only initial concentrations are given. We solve the second type by creating an ice table and using a variable x to represent the change in concentration. Equilibrium is so important. When a system at equilibrium is disturbed by a change in the amount or reactant of a reactant or product, a change in volume or change in temperature, the system shifts in a direction that minimizes the disturbance. So, ladies and gentlemen, it was an exciting match. At the end, the scoreless first half and three huge goals in the second, including the Chatelier's winner at the wire. The classical goes Equilibria's way on enemy ground, and all the reactions continue until we meet again for the classical Acidica and Basisio. Hope you're doing well. Hope all is well. Continue to read, continue to study, continue to prepare. This is just a preview of more to come in terms of equilibria, acids and bases, dynamic equilibria, and other concepts associated with thermodynamics. Good evening, students. It is so good, so exciting to have you in lecture today. It's definitely a privilege, an honor. It is a treat. Just want to remind everyone, you are not alone. This is an academic community. Remember to get help from university services if needed. Never give up. Never give up. Keep trying. We're here to help you be intelligent, successful, and responsible scientists. However, at the end of the day, you must be responsible, intelligent, and hardworking. I want to remind you, don't give up. It may be challenging, it may be hard. Find strategies, find resources, meet with people, network, do what you can. It's worth it. You are smart enough, you are good enough, You are worth the effort and the fight. Keep it up. So, today we're going to be going through a few advanced topics. I just want to give you a quick preview of some organic chemistry ideas. It's very valuable, very useful, and I think it'll be a good resource for you. This book was written by myself and reviewed by one of my good colleagues and friends, Vincent Miranda. So it's dedicated to the tens of people who have helped and inspired me, specifically my parents, Doctors Ferguson, my brother, attorney Ferguson, and my sister. It's definitely, and his wife as well, my brother's wife as well, and those teachers in university and high school who helped make science accessible to me. So let's just go over it. Organic chemistry is a subject that requires effort, focus, and skill. These foundations have been selected after guided review and observations as to what concepts facilitate and support a good understanding as a student progresses through this discipline in chemistry. These foundations, from the moiety to the metallics, highlight with conceptual focus key ideas, points, and memory aids to support your success in organic chemistry. Learning organic chemistry is similar to building a house. It takes time, skill, and persistent efforts. So let's begin. Of course, this will be an audio and a visual as well, depending on how you learn. The goal for this episode is to encourage those who are studying organic chemistry. I know from personal experience that organic chemistry can be at points, especially organic chemistry 1, challenging because you're adjusting to a new paradigm per se, and you are adjusting to a new set of content. But the thing you have to remember is with strategy and persistence, you can make it through it and do well and do your best. So, some objectives that we want to remember. We want to learn the key definitions. We want to understand key ideas and the relevance of Lewis-Dot structures, and we want to understand some simplified quantum mechanical concepts. Organic molecules can be defined as multiple atoms associated or bonded together, made primarily from carbon. In short, organic molecules are carbon-based molecules. So we have the structure of cyanocobalamin. This is the structure I did my undergraduate thesis on, also known as vitamin B12. These molecules may or may not have the same molecular formula. In cases where the molecular formula is the same but the structure is not the same, you have structural isomers. Some examples include acetone and dimethyl ether. Note, when the constitution or the connectivity is not the same, you have constitutional isomers. Where the arrangement in 3D space is not the same, you have stereo isomers. In some instances, constitutional is sometimes interchanged with structural isomers. Now, subclasses of stereoisomers. You have optical isomers, which are molecules that rotate light differently, and their mirror images are non-superposable, otherwise known as enantiomers, and they are designated by E, Z, R, or S, Intagon, Zusammen, Rectus, or Sinister. Geometric isomers, which are molecules that have non-identical mirror images, there would be a cis and trans. The arrangement around the plane of the double bond is different. Organic molecules can be linear. Linear molecular shape is observed with hydrogen cyanide or acetylene, or it may be planar, but trigonal, such as formaldehyde. A bit of formaldehyde, the structure for formaldehyde is cut off. The other hydrogen. Also, the molecule can have a 3D arrangement such as methane, existing as a tetrahedral molecule. So it's important to remember that molecules are multiple atoms bonded together, and compounds are a type of molecule in which you have multiple heteroatoms bonded together. So the atoms are different in that case. So let's talk about the structure of 3D molecules. The structure of 3D molecules can be predicted using an application of correctly drawn Lewis-Dot structures, which is valence shell electron pair repulsion theory, also known as Glepsin-ion theory. VESPA, that's one way to say it, involves valence bond theory, showing all valence electrons and including bonding and non-bonding electrons, in some cases referred to as lone pairs, and maximizing separation in 3D space so as to minimize repulsions. connected to Coulomb's law in that greater distance minimizes potential energy. So greater distance between like charges minimizes potential energy. And the converse is true in that when you increase or decrease the distance between unlike charges, you also minimize potential energy. So VESPA is an alternative that can inform and start the journey in us understanding molecular geometry, whether it be the linear alkynes, the trigonal planar arrangements of the carbon atoms in some alkenes, or the tetrahedral arrangement of carbon atoms around some carbon atoms in alkanes. Another alternative involves using quantum mechanics that uses wave functions that are mathematical descriptions of electron probability distributions to produce atomic orbitals. There are some limitations in this method as it pertains to accuracy, as with the previous method, VESPA, considering the theoretical simplifications that I use. Overall, the goal is to gain a better understanding as to what occurs in nature. For example, with quantum mechanics, we can step into hybridization theory and use mathematical mixing of wave functions to further our understanding of what is observed in nature. With the same goal, through ideas of valence bond theory, we can predict the bond angles for methane, specifically the intermolecular H-H bond angle in methane, hydrogen-hydrogen bond angle in methane. There are deviations, however, that are observed, and hybridization accounts for those deviations with explanations. Those explanations entail the ideas that linear arrangements have carbon atoms that are sp hybridized, 1 sp plus 2 p's. Trigonal planar arrangements have carbon atoms that are sp2 hybridized, 1 sp2 plus 1 p. And tetrahedral arrangements have carbon atoms that are sp3 hybridized, 1 sp3 plus 0 p. Other hybridizations occur less frequently in mainstream organic chemistry. However, with higher geometries common with inorganic compounds, there can occur trigonal bipyramidal sp3d or octahedral sp3d2. So note, quantum mechanics also involves the use of molecular orbital theory to understand other interactions, but that will be discussed later. With the same focus, quantum mechanics also enables chemists to speak on regional electron densities. Also, it's important to know that double bonds possess a sigma bond and a pi bond, and triple bonds have 1 sigma, 2 pi. So some questions you want to think about. What is organic chemistry and what is the historical origin of it? What is one class of organic compounds? What are 3 different types of isomers? Explain the valence bond theory in general simple terms. What is one molecular example where valence bond theory does not accurately explain what occurs in molecules? What are the hybridization of carbon atoms in acetonitrile? What are the designations of sigma and pi for the bonds in acetonitrile? So let's keep going. We're going to have a quick break and then we're going to continue talking about functional groups and other ideas. Okay, so let's go. Functional groups and other ideas. So you want to understand what is a functional group, understand the key format for organic nomenclature, and understand the role of intermolecular forces. Functional groups are characteristic parts of molecules that convey specific chemical properties to the molecules that possess them. Functional groups do numerous things, but mainly they enable us to compartmentalize information about molecules, compounds, and reactions. Functional groups do give us insight into chemical interactions, such as intermolecular interactions, as well as give us more information in understanding the properties of molecules. This includes the physical properties, boiling points and melting points, and solubilities. Considering the usefulness of functional groups, they also possess a characteristic molecular fingerprint that is detected in many ways, namely in spectra, so IR spectra, which really gives you a fingerprint as to the functional groups within a molecule, and that'll be discussed later. So case in point, we have an example of phenol right there. So we have types of molecules and their properties. There are several types of molecules in the world. However, in the discipline of organic chemistry, There are specific molecules that are discussed frequently, including these. You have your alkanes. Alkanes, otherwise known as paraffins, are saturated hydrocarbons and aliphatic compounds. These molecules form a series of homologs with a repeating methylene unit and with the general formula CnH2n plus 2 and ending with the suffix -ane. For example, in increasing order from 1 to 5, we have methane CH4, ethane C2H6, propane C3H8, butane C4H9, pentane C5H12. The following prefixes are hex for 6 carbons, hept for 7 carbons, oct for 8 carbons, non for 9 carbons, dec for 10 carbons. These prefixes from meth to dec are applicable throughout the naming of organic compounds, alkanes, alkenes, alkynes, alcohols, etc. And there are lots of ways you can code this information, even when it comes to heterocycles, whether it be ir, et, dash, ep, ir, et, dash, ep. So there are lots of ways you can code the information for different heterocycles. We can discuss that, chunking on that mnemonic later. So ir, oxirane, oxetane, oxane, oxalane, oxeptane, all those things. We can discuss that later. So alkenes, otherwise known as olefins, are unsaturated hydrocarbons and they are considered aliphatic compounds. They contain at least one double bond, forming a homologous series with the formula CnH2n. These are alkenes now. These molecules end with the suffix -ene. So alkynes, otherwise known as acetylenes, are unsaturated compounds having a triple bond. These molecules form a homologous series with a general formula CnH2n-2. These molecules end with the suffix -ine. There are several other molecules that form a homologous series within their groups, including carboxylic acids and aldehydes. You also have alcohols. Alcohols whose main functional group for identification is the hydroxyl group. It is notably priority in nomenclature practice. Exceptions include carboxylic acids according to the IUPAC. Alcohols contain one or more hydroxyls forming a homologous series, CnH2n plus 1 OH. Alcohols are aliphatic and typically end with the suffix -ol. So let's talk about intermolecular forces and other properties. With functional groups comes certain properties such as specific boiling points and melting points, as well as critical temperatures. The temperature around which a vapor does not easily undergo a phase change to a liquid, and many other physical properties. However, beneath the surface of physical properties are the chemical features or interactions known as intermolecular forces, which influence and enable comparative predictions and physical properties. Namely, there are key forces to remember. You have your dipole-dipole forces. These are forces which occur between molecules, intermolecular, with a dipole moment or a significant dielectric constant. These molecules are otherwise known as polar. These intermolecular forces, IMFs, are relatively strong. A relatively stronger version of this is the H bond or hydrogen bond intermolecular force. So you have your hydrogen bonding. It is a stronger force, sometimes referred to as a strong dipole-dipole force. This is a relatively strong, some consider it the strongest, of the IMFs. It occurs in water and other molecules with hydrogen bonds to nitrogen, oxygen, and fluorine. Then you have your ion dipole. This occurs between ions and polar molecules, for example with solvation of sodium chloride crystals in water. Then you have London dispersion forces. London dispersion forces occur in all molecules and are based off of the Coulombic interactions between transient, in essence temporary, dipoles. These electrostatic forces result in transient interactions between molecules. Then you have van der Waals forces. Now a weak force that consists of two kinds, including the van der Waals force, which is discussed in short, is where more elaboration can be found in other texts, in other episodes. It is worth noting that IMFs and their strengths are based off of functional groups, chemical structure, and the types of chemical bonding in those molecules, so intermolecular bonding. So what's inside influences what occurs on the outside. Composition influencing function. Anyway, chemical bonding, you have polar covalent bonding. Covalent bonding occurs between atoms with significant electronegativity differences. So this is polar covalent bonding. Specifically, this bonding occurs with heteroatoms, which refers to different non-metal atoms. So different non-metal atoms. Many times the Pauling scale is used as a reference for ranges to determine the type of bonding arrangement occurring between atoms. If bonding, though considered a theoretical construct, is viewed on a spectrum, polar covalent bonding would exist around the middle. Then we have covalent bonding. This is also non-polar covalent bonding. This is almost at the another end of the bonding spectrum, where there is less significant difference in electronegativity. So then you have ionic bonding. This is at the other end of the bonding spectrum. This occurs between metals and non-metals. For example, in sodium chloride, there's a large difference in electronegativity. Solvation. Solvation is dependent on many factors, including the principle like dissolves like, and ideas such as hydrophilicity and hydrophobicity. Hydrophilicity and hydrophobicity. These terms refer to the molecule's stance in relation to water, whether it has a significant affinity for water, hydrophilic, water-loving, or less significant affinity for water, hydrophobic, water-hating. The tendency of molecules is as follows. Polar and ionic compounds tend to be hydrophilic compared to covalent and non-polar compounds, which tend to be hydrophobic. Nomenclature, according to the IUPAC, is based off of four main parts: prefix, locant, parent chain, suffix. The prefix, this normally denotes the number of each substituent or functional group attachments. Prefixes include di, tri, tetra. The locant, which is the number that describes the functional group attachment or the substituent's position. The parent chain, this is normally the longest continuous chain in the molecule. The suffix, this is based off of the presiding or prioritized functional group, chain, or bonding arrangement, single, double, or triple. Suffixes are typically classical in ending, with ane referring to alkanes, ene referring to alkenes, ine referring to alkynes, amine, amines, amide, amides, oic, carboxylic acid, ate, esters, one, ketones, dehyde, aldehydes. Key facts to note: the alcohol's functional group hydroxyl is normally prioritized overall. Substituents are transcribed or outlined in the name based on the relative alphabetical order, so ethyl before methyl, and that pattern continues. So key overall idea, and I'll repeat this twice: prefix, locant, parent chain, suffix. Prefix, locant, parent chain, suffix. Prefix, locant, parent chain, suffix, generally. So you can look up further ideas about IUPAC nomenclature in other texts. So some questions to consider: what is a functional group, and name several examples of functional groups? What are three types of organic molecules? What is an intermolecular force? Explain dipole-dipole forces. What is one molecular example where intermolecular forces explain a physical property such as boiling point? What is one difference between hydrogen bonding and London dispersion forces? Explain the overall process of naming simple organic compounds. So if you want, just an aside, quick aside, you want more information into heterocycles, there's a phenomenal chemist, his name is Dr. Barron. He has lots of resources out there for heterocycles. So feel free to look into that. Very good resource, very brilliant chemist. So let's keep going. Concept development 3, structures, conformations, and projections. So one things we want to do, and also just remember this episode is primarily dedicated to those in general chemistry as well as those who are in organic chemistry, with the thrust that we want to encourage and help each other as we go along in our scientific careers. So, objectives. Understand and be able to draw Lewis electron dot structures, condensed structures, and bond-line structures. Understand and be able to draw different conformations, primarily those of cyclohexane. Understand and be able to draw and identify Fisher projections and Newman projections. So structures are diagrammatic representations of different molecules, and they provide a means of understanding what is occurring in nature. There are a variety of different structures used in chemistry. The main examples in this episode would be Lewis electron dot structures, condensed structures, and bond-line structures. So Lewis dot structures, named after your boy Gilbert N. Lewis, a brilliant scientist. They are built on some key ideas such as the Adams valency and the octet rule. There are specific exceptions for period 3 with sulfur and arsenic, for example, and beyond. Valency. Valency refers to the amount of electrons an atom will lose, many times resulting in a positively charged ion cation. Gain, many times resulting in a negatively charged ion anion. Or share, typically occurring in covalent molecules, in order to have a stable noble gas configuration. Ground state, of course. Valency can be determined using the periodic table. The group number, the vertical column numbers for main group elements, typically in the periodic table, is designated the valency. The valency corresponds normally with charge, oxidation number, and its subsequent sign is dependent on the type of atom, its reactivity, and what it is reacting with. So, key points to note. Valency can be shown quickly using Lewis dot structures and orbital arrangements. Can be explained simply, in some ways, with the Bohr model. The octet rule now. The octet rule is a principle with applications in resonance theory, simple chemical mechanisms, and reactions. The octet rule is based on the idea of atoms gaining, sharing, or losing electrons in order to have a complete octet. And in this context, we're referring to 8 outer electrons. There are exceptions. For example, some atoms may lose electrons to possess the electron configuration of helium, 2 outer electrons. However, for the most atoms, in period 1 and period 2, in the periodic table of elements, those elements obey the octet rule generally. This rule is helpful in predicting reactivity and explaining simply the rationale for certain chemical reactions. So from period 3 onward, there are exceptions. So let's think about the rules for writing Lewis electron dot structures. So NP-SEM, note the total amount of valence electrons. Place single bonds between each atom. Subtract 2 electrons for every single bond added. Eliminate or note the remainder amount of electrons. And minimize formal charge as best as possible. So for atoms and ions, consider the group number primarily an electron configuration. For molecules, start by determining the total electron count among the atoms in the molecules. Draw single bonds between each atom. Subtract 2 electrons for each single bond. Add extra bonds when necessary. For example, carbon-oxygen bonds in aldehydes and ketones. Bonding arrangement is typically in the form of a double bond. Ladies and gentlemen, you must know and observe the trends. After all the necessary extra bonds have been denoted, subtract the correct amount of electrons for the extra bonds added. Typically, with the remaining electrons, denote them as lone pairs around the relevant atoms. So let's keep going. Condensed structures. Condensed structures are important in the process of understanding what bond-line structures represent and show. In condensed structures, all of the hydrogen bonds are attached to the carbon. For example, S2 bromobutane, you can see here. So bond-line structures are the next step after condensed structures. These show only the carbon framework with each carbon represented by a bend in the chain, and the hydrogen not denoted, but inferred or assumed to the point or a complete octet around the carbon atom. This means that hydrogens are not shown, but implied to the point that the valency of carbon is satisfied. For example, we see there, bond-line structures are useful and efficient. They save time. You can see the example of a bond-line structure right there for benzene. Now conformations. Conformations are molecules that differ only by rotations around single bonds. You may have heard of conformers, rotamers, otherwise characterized as sigma bonds. These alternate rotations affect the potential energies of the molecules, either increasing, as seen in the eclipse conformation, or decreasing it, as seen in the anti-conformation. Conformation's potential energies are attributed to ring strain, which is based off of the angle strain and the torsional strain. Angle strain is caused by the alternate bond angles that have deviated from the idealized bond angle suggested in Vespa. Torsional strain is caused by repulsion due to the dispersion forces, an intermolecular force, and this can cause steric hindrances. So as you progress further in your career in science, you'll hear the two whistling concepts, two echoing concepts in the halls of organic chemistry. You have sterics and electronics. So conformations can be experimentally described using a graph of dihedral angle versus potential energy. As you study this some more, you encounter things like Karplus correlation, all of that, a lot of good stuff. So typically cyclohexane is plotted showing the potential energy of the different conformations in there or in increasing potential energies. The chair, the twist boat, the half chair, and the chair. Chair, twist boat, chair, half chair, twist boat, half chair, chair. It's important when you start learning about this to be able to draw your chairs correctly. Chair, half chair, twist boat, twist boat, half chair, chair. So CHT, BTHC. CHT, BTHC. Chair, half chair, twist boat, twist boat, half chair, chair. Projections. In chemistry, there are many types of projections. However, two that are frequently encountered are the Newman projection and the Fisher projection. So Newman projections are structures from a specific perspective. We look down a specific single bond between atoms and draw the other attachments in respect to those two atoms. For example, butane is drawn. So picture yourself looking down the axis of a single bond, C2 to C3 of butane, or C2 to C3 in some other molecule. In order to draw the Newman projection. Here we see an example of a Newman projection. Then you have your Fisher projections. These are typically seen with your carbohydrates and your hexoses and all those other good stuff. They involve another representation from a different perspective. The molecule is drawn from top to bottom, normally with the anomeric carbon at a designated end. Generally, the functional group attachments are on the sides, which are seen as wedges that are out of the plane of the paper, and the top and bottom of the projection is seen as groups on the dashed. Another bond designation uses a squiggly line, which represents a single bond out and behind the plane of the paper. So the projection is typically used with carbohydrates, especially simple carbohydrates. So you can see an example of R, 1 bromo, 1 chloroethane, and then you can see another example of thalidomide. Classic molecule, as is also discussed when we introduced the key ideas associated with stereochemistry and how important it is even when it comes to medicines, their use and effects in the human body. So let's talk about some questions. What is the Lewis electron dot structure of oxygen? What are the key ideas for drawing Lewis electron dot structures? Explain the concept of valency. Explain the octet rule. What is one exception to the octet rule? Draw the bond line structure of antizine. Explain the overall order of stability for cyclohexane conformations. Remember, we go chair, half chair, twist boat, chair, half chair, twist boat, twist boat, half chair, chair. Chair, half chair, twist boat, twist boat, half chair, chair. CHTBTHC. CHTBTHC. For those who need to know that. Okay, so let's talk about chirality and isomerism. You want to know key definitions. Definitions of words such as isomer, chiral, and conformers. Understand the concepts of stereoisomerism, chirality. Understand the Lebel-Van 't Hoff rule. So let's keep going. Isomers, as defined earlier, are molecules with the same molecular formula but different in structural arrangement, space, connectivity, or geometry around the bonding arrangement. All those differences aforementioned define a subclass of isomers, be it structural, so structural isomers, arrangement in space, stereoisomers, or connectivity, constitutional isomers. Each subclass has its own significance. Stereoisomers or spatial isomers are molecules with the same molecular formula but different three-dimensional spatial arrangements. A stereoisomer has a stereogenic center, which is a location in the molecule where the interchange of two groups in space results in a new stereoisomer. A subgroup of stereogenic centers is a chiral center, which typically refers to a stereogenic center with a sp3 hybridization or tetrahedral geometry. Every chiral center is a stereogenic center, but not every stereogenic center is a chiral center. Stereoisomers can be further divided into other categories such as enantiomers, non-superposable mirror images, diastereomers, non-identical mirror images, atomisomers, isomers as a result of restrictions in bond notations. So enantiomers are optical isomers. These optical isomers are molecules that are non-superposable. Enantiomers typically have chiral centers, or a chiral center. Enantiomers are very significant in the pharmaceutical industry, with specific enantiomers in drugs having specific effects. This is seen with the classic example of thalidomide, ibuprofen, and Darvon, where stereospecificity contributes a large role in determining therapeutic potential and therapeutic effects. Enantiomers are typically designated by the signets of absolute configuration, which are R rectus and S sinister. Mixtures of both enantiomers are called racemic. Usually these are mixtures of equal proportions. The process of forming both enantiomers as products is known as racemization. And if you do some more research, you'll hear about Viedma ripening. You can do the research and find out about it. So the molecules are also designated by the relative configuration, which are dextrorotatory D and levorotatory. And that refers to their optical rotation, how they rotate light. So let's talk about assigning configurations. Dextrorotatory or levorotatory must be assigned experimentally, typically by the proper application of an optical device such as a polarimeter. To observe and measure how the molecule rotates light and to what extent or degree it rotates it. Absolute configurations can be assigned using a priority numerical labeling system such as the Kahn-Ingold-Prelog priority rules. These rules give priority based on atomic mass. Larger atoms have the highest priority, and the smallest or least weighing atoms have the least priority, typically hydrogen in most molecules. So if you have hydrogen, typically it's going to be on the dash. Okay, in the back of the plain of paper. And then your largest priority, thing that has the highest priority, is going to be coming out at you. Okay, so there you have S1 bromo 1 chloropropane. So let's talk about diastereomers. This is a subclass of optical isomers. A subclass of optical isomers, known as geometric isomers. Diastereomers are isomers with the same molecular formula but different arrangements in space. That results in non-identical mirror images. These can typically be identified by first assignment of the absolute configuration of the stereogenic centers, then comparison of the mirror images to determine whether they are identical or not. So that's a suggested way you can do it. Subclass of diastereomers are cis-trans isomers and conformers, which can further be divided into rotamers. So you have your easy isomerism and your cis-trans isomerism. As dextrorotatory and levorotatory is relative assignment for stereochemistry, so is cis and trans. Cis and trans isomerism allows for the denoting of the spatial arrangements based on like groups, for example, trans 1,2-dichloroethene or cis 1,2-dichloroethene. This relative system, cis or trans, can become obscure very quickly. So to provide a more meticulous system, the Kahn-Ingold Prelog priority rules are used to label the substituents on the double bond using antagon, E or opposite, and zusammen or same side. So antagon, E opposite, zusammen, same side. This system, aforementioned, provides more clarity with stereochemistry. As stated earlier, the Kahn-Ingold Prelog priority rules give the highest priority to the largest substituent or the substituent with the greatest atomic mass, and the following substituents are labeled with the numbers 2, 3, 4 based on atomic masses. So you number your substituents. Basically, you assign your priorities, you number your substituents. It's good to do this with your modeling kits, your modeling sets, and if you can't afford it, you can use gumdrops and toothpicks. And just make sure you use different colors for different types of atoms. But assign your priority, arrange it, visualize it in 3D space. You may have to build a model. And from there, you see 1, 2, 3, 4, rectus, 1, 2, 3, 4, sinister. If it goes clockwise, if the substituents are ordered such that they go in a clockwise way, rectus. If they go or they're arranged such that they follow a anticlockwise path or trajectory, we call it sinister. So conformers and rotamers. A conformer is an arrangement or conformation of a molecule based on a rotation of single bonds that resulted in a potential energy minimum. A classic example of a conformer is with cyclohexane, which you have different conformers represented in the graph below. A rotamer is just a conformation of a molecule that results from another rotation of a molecule's single bonds. And you have the anomers, automers, and isomer formed due to the geometric variation found in certain atoms in specific molecules. Anomers are typically seen and described in carbohydrates where the designation of alpha or beta is used. Alpha D-glucopyranose, beta D-glucopyranose. And you have the epimers. An epimer, normally found in diastereomeric pairs, is a stereoisomer that differs in configuration at any point in the molecule where changing the position of the two substituents results in the formation of a new stereoisomer. Basically, an epimer is an isomer that differs in configuration at any stereogenic center. So Libelle-Van 't Hoff rule. If there are n stereogenic centers with 4 different substituents attached, there are 2 to the n different stereoisomers possible. So if you have n stereogenic centers, there are 2 to the n different stereoisomers possible. Okay, so some questions to think about. What is an isomer? What are the different types of isomers? Explain the concept of enantiomers. What is a racemate? And even further research, you can look into what is V-amer ripening. Then you can talk about, or just look into what is a diastereoisomer. What are 2 subclasses of diastereoisomers? And then we can talk about explaining the Kahn-Ingold Prelog priority rules for designating absolute configuration. So let's keep going. Nucleophilicity and electrophilicity. In it for the long run. Learn the definition of nucleophilicity and electrophilicity. Understand the trends with nucleophilicity and basicity, or electrophilicity and acidity. So we want to understand those things. Those are our objectives for this reading. Nucleophilicity is a kinetic concept that describes the affinity of an atom or molecule for the nucleus of another atom, which is positively charged with the intended meaning of nucleus loving. So nucleophilicity, nucleus loving. This term is very important for understanding reactions and their mechanisms. Nucleophilicity refers to how willing, to what degree, or at what rate is an atom or molecule donating its electron density to another atom or molecule. The degree of nucleophilicity is defined by the rate of the reaction, specifically the rate of electron density donation. Generally, nucleophilicity, when comparing a similar atom in multiple molecules, follows Lewis basicity for some contexts. Also, when a nucleophilic atom is different, there may be no relationship between nucleophilicity and basicity. So that's something to note. If the nucleophilic atom is different, there may be no relationship that you observe. Since dipole moments for each atom or molecule may be different, thus affecting polarizability, which is a large determining factor in nucleophilicity. So polarizability of the electron cloud is a large determining factor in nucleophilicity. So it's very important to understand it. It's grounded in Coulombic. It's grounded in Coulombic forces. It can result in the formation or breaking of bonds, as seen in the infamous nucleophilic attack and nucleophilic substitution. So let's talk about electrophilicity. Electrophilicity is a kinetic concept. It involves a reaction in which there is an acceptance of an electron pair. An electrophile is defined as an electron pair acceptor or an atom or molecular part that is electron-loving, electrophile. This term provides insight into mechanisms or reactions such as electrophilic aromatic substitution, electrophilic substitution, and electrophilic addition. Electrophilicity it basically involves the measured degree or extent, generically speaking, of how much an atom or molecule is willing to accept electron density from another atom or molecule. So, some questions to consider. What are some key ideas associated with the concept of nucleophilicity? What are some key trends with nucleophilicity? Explain the connection between Lewis basicity and nucleophilicity. What is the connection between Lewis acidity and electrophilicity? Explain the significance of pKb, some aspects of the concept of nucleophilicity. So let's talk about spectroscopy and some instrumentations. Spectroscopy involves the study of the interactions of electromagnetic radiation and matter. Spectroscopy has a key role in organic chemistry. It contributes to informing many processes, including retrosynthetic analysis, structure elucidation, and total synthesis. Spectroscopy and spectrometry are different. Spectroscopy refers to the study of the interaction of electromagnetic radiation and matter, while spectrometry refers to the measurements of the interaction of electromagnetic radiation and matter. So measurements versus just the study. We have UV spec. That's an example of a diagram. UV light source going to your scanning monochromator, a UV motor that's spinning. It goes to the sample cuvette, and you go to your detector, you amplify it, and then it's displayed. For your sample cuvette, you also have a reference cuvette as well. So UV-vis spectroscopy is an analytical technique that involves the use of ultraviolet or visible light in order to analyze a sample in a cuvette. This technique can be used to quantify, detect, test, support structure elucidation, and aids in determining molecular geometry and to study the kinetics of reactions. So when you think of UV-vis spec, also think about Woodward-Hoffman rules. One of the main ideas behind the use of UV-vis spectrophotometers is the principle of absorbance. You can look into Bayes' law, and also you can look into Bayes' law. Absorption is equal to epsilon molar absorptivity constant, B path length, C concentration. Then you have atomic absorption spectroscopy. AAS, go from your light source to your sample to your detector to your computer. It has many uses involving clinical, geological, biological, metallurgical, atmospheric, and also in the pharmaceutical industry. Then you have your IR spec. You go from your Nernst glow, this is just a version of it, to the Michelson interferometer, to your sample, to your detector, to your computer. So IR can be used to detect the functional group moieties that exist in the sample, the relative location or proximity of the information, the relative location or proximity of functional groups. That information can be obtained. It's based on the assumption that atoms behave as simple harmonic oscillators, that each vibration is occurring within the molecule. You have your NMR spec, in which you go from your RF radiation generator to your NMR tube, to your RF receiver, to your computer. NMR spec provides information on the chemical environment the nuclei of atoms are situated in. This type of spec is normally used in structure elucidation and in some cases structure determination. This analytical technique involves several concepts, some such as shim, all this other good stuff. So gas chromatography. mass spectrometry. You have your GCMS, you go from your sample holder to your capillary column, to electron ionization, to your ion trap, to the computer. It's an analytical technique that involves both analytical techniques of gas chromatography and mass spectrometry. This is a method in which components of a mixture are separated using chromatography and analyzed and characterized using mass spectrometry. Gas chromatography is a separation technique in which chemical substances are volatilized and separated by their relative boiling point, which is dependent on the chemical properties of the molecules. Mass spectrometry is an analytical technique that involves the ionization of chemical species into different ions of different atomic masses and the sorting of ions into a unique spectrum based on their mass to charge ratio. So some key features are, what are some key features of a UV-vis spectrometer? What are some key features with the infrared spectrometer? What is the Jacquinot advantage, so throughput advantage? Explain Felgate's advantage, multiplex advantage. Explain the differences between polar and non-polar compounds in the GCMS instrument. So we can talk about inorganic and organic metallics. This is the first part. Diatomic halogens have chemical significance as seen in several areas of organic chemistry. Whether in the presence of light, organic solvent, or peroxides, they can result in the formation of halogenated variable groups, which can vary from alkyl halides to acyl chlorides. Diatomic halogens, when substituted in the organic molecule, can result in new properties, both chemical and physical, stereochemistry, intermolecular forces, as well as conformations. Also, the chemical reaction environment also affects radioselectivity in the reaction. Also, diatomic halogens can be used to test for the presence of olefins, namely bromine methanalkene, and the result is a colorless solution. Diatomic halogens have versatile use in organic chemistry. So, several inorganic reagents are used as reducing agents or oxidizing agents to convert carbonyl-containing compounds in primary and secondary substituted hydrocarbons to primary and secondary alcohols, and in another direction it can convert alcohols to carboxylic acid. You have your sodium borohydride, used to do a stepwise reduction from aldehydes to ketones to alcohols. You have LiAlH for lithium monohydride, very dangerous, flammable and powerful reducing agent that reduces carboxylic acids and other carbonyl containing compounds to alcohol. So you have PCC, pyridium chlorochromate, which is used to oxidize. It functions to oxidize primary alcohols to aldehydes and secondary alcohols to ketones. Pyridium chlorochromate is made by reacting chromium trioxide with hydrochloric acid to form chlorochromic acid, which is reacted with pyridine to form PCC. Then you have the Jones reagent. It is an inorganic reagent that is used to oxidize. It functions typically as chromic acid and involves oxidizing primary alcohols to carboxylic acids and secondary alcohols to ketones. The Jones reagent is a good oxidizing reagent. Then you have KMNO4, potassium permanganate. There's another inorganic reagent that results in the oxidation of primary alcohols to carboxylic acids and secondary alcohols to ketones. Always remember or consider the temperature at which that oxidation is occurring. Very important. Then you have PCl5, a molecule with many uses, namely the interconversion of carboxylic acids and acid anhydrides to acyl chlorides. Then you have sodium cyanoborohydride. It is used in reductive amination, resulting in the formation of amines from the reduction of the cyanide portion of the reagent. There are some rearrangements that occur when this is taking place. This is another example of nucleophilic attack occurring. Meanwhile, sodium borohydride is serving as the infamous reducing agent. So some organic metallics, you have your Grignards. Grignard reagents are some of the first encountered organic metallics for an undergraduate organic chemistry student. These molecules are composed of an organic variable group, a magnesium atom, and a halide. These are normally used to attach organic variable groups to a carbonyl, meanwhile reducing the oxygen to a hydroxyl, thus making an alcohol. Grignard reagents are very useful, however, because these are reactive even with water. All material used in the reaction to avoid water contamination must be lab oven dried. Then you also have Gilman reagents. Given reagents are organocuprates attacking as a nucleophile to rings with an unsaturated reagent, alkenyl, or to an alkyl halide to form an alkyl substituted molecule. Then you have your regular nucleophiles, such as metallic alkoxylates, such as sodium ethoxide, magnesium ethoxide, which are used as nucleophiles to attack a variable group, whether in an SN2 or E2 manner, as well as in displacement reactions. So, here are some questions. What are some examples of substitutions using diatomic halogens? What is an example of an oxidized alcohol? Explain the use of sodium borohydride in reduction reactions. Where does the organoborane occur in the reaction schema, and why is this chemically significant? Can nucleophilic attack serve as a means of oxidation or reduction? So let's talk about some regiochemistry principles. Understand the fundamentals of regiochemistry. Understand Markovnikov's rule and anti-Markovnikov's rule. So Markovnikov's rule, he who has more gets more. Anti-Markovnikov, he who has more gets less. Understand Zaitsev's rule and Hofmann's rule. So let's keep going. This will be the last section that we go through today. More to come later on. So regiochemical principles regiochemistry comes from the Latin word regionum, meaning direction. Regiochemistry provides and describes the principles involved in the directionality or position and placement of reactants to form the product. Regiochemistry is very important. As you progress, you'll hear about things being regiodivergent or regioselective. Reagents used can cause a specific regiochemical result or result in the opposite of what would normally occur. So you have Markovnikov's rule. Put simply, he who has more gets more. Markovnikov's rule is in the addition of a halide to an unsymmetrical alkene, the hydrogen goes to the carbon with the greatest number of hydrogens, and the halide goes to the other carbon. In another way, this rule states that the halide adds so as to form the more stable carbocation intermediate. Then you have your anti-Markovnikov, which is the reverse, he who has more gets less, in which the carbon with the greatest number of hydrogens does not receive the hydrogen but the most electrophilic portion of the molecule. For example, in hydroboration oxidation, in the presence of peroxides, the borohydride adds to the less substituted carbon of the hydrogen, and the hydrogen adds to the more substituted carbon. Keep in mind hydroboration oxidation, which this is done in the presence of peroxides. Or in this case, we're referring to it being done in the presence of peroxides. However, the stability comes about because the electron density shifts. This is one way to describe the mechanism. The electron density shifts to the electrophilic borohydride, resulting in it possessing a partially negative charge, and the more substituted carbon possessing a partially positive charge. This is indeed stable due to the electron density during the incapacity of the alkyl group. In the discussions, we can talk about hyperconjugation. S character and the orbital overlap of the alkynyl carbon. The alkynyl group with the alkyl or electron-donated substituent provides stability. So, Zaitsev's rule. Zaitsev's rule is the directionality principle in which the more substituted alkene is favored through the use of a small base such as ethoxide. Zaitsev's rule is significant and aids in predicting products in elimination reactions. So Zaitsev's small base used to the more substituted alkene. So Zaitsev's small and more substituted. So Hofmann's rule. Hofmann's rule is another directionality principle. So T. Hofmann, in which the less substituted alkene is favored through the use of a huge or large base, such as tert butoxide. Hofmann's rule is also very significant and aids in predicting elimination reactions. So the Hamann-Leffler postulate. In simpler terms, it's basically the view on the potential energy hill continues in some ways as you follow through the potential energy journey, or the product resembles a molecular arrangement of the transition state, or the step of the RCD, the reaction coordinate diagram, that's closest to the transition state in energy. Typically, the transition state will resemble that. So what does the word regiochemistry mean? What's an example of a reaction that follows Markovnikov's rule? Explain Antimakovnikov's rule. What is Zaitz's rule significant? Why is it significant in elimination reactions? Explain the significance of the Hammond-Leffler postulate. Why are physiochemistry rules helpful in studying mechanisms? So types of reactions. Let's just go through these. You have your addition, substitution, elimination, reduction, oxidation, and rearrangement. Addition, put simply, is like a traditional synergistic relationship. The two parts become one. Two different molecules are added together. Addition can be driven by nucleophiles, nucleophilic addition, or electrophiles. This type of reaction normally occurs in regions of high electron density and bond order, which is seen in compounds with multiple bonds. You have your substitution. Substitution is by definition a type of chemical group replacement. This can be driven by nucleophiles or electrophiles, as well as it can involve alkyl halides or aromatic compounds, SN1s, SN2s, typically some of the first reactions encountered by an undergrad in OChem. Then you have eliminations. Eliminations involve the loss of a group of atoms from a molecule. This can result in the formation of an alkene or alkyne product. Elimination tends to result in a net increase of electron density for a particular molecule, which, if considered, makes sense, since the overall process of loss and gain of electron density is usually presented mechanistically. Then you also have reduction and oxidation. Classically paired process in which one atom or molecule gains electron density while another loses electron density, which is reduction and oxidation, respectively. So oil rig, oxidation, loss of electrons, addition of oxygen, removal of hydrogen, increase in oxidation state or number. And then GLAD, gaining of electrons. Reduction is GLAD, oxidation is Larry. Reduction, GLAD, gain of electrons, loss of oxygen, addition of hydrogen, decrease in oxidation state or number. So you have reduction occurs in organic reactions such as hydrogenation using uranium nickel or lithium hydride. Then you also have your rearrangements, which typically occur through your 1,2 methyl shifts or 1,3 methyl shifts or 1,2 hydride shifts or 1,3 hydride shifts. The thermodynamic basis and rationale for these rearrangements occurring is that they lead to a more stable carbocation as a transition state or reaction intermediate. Many times the rearrangement results in positive charge being situated on higher substitute carbons. This is presented as secondary or tertiary carbons. There are other categories for mechanistic classification. Polar under basic conditions. Example is a nucleophilic substitution under basic conditions. Polar under acidic conditions. An example is an acid catalyzed hydration. Sorry about the background noise. You have paracyclic. An example is the 4+2 cycloaddition. Deals all the reaction. The 4+2 reaction refers to the number of electrons, specifically pi electrons. And you can look into Huckel's rule, each atom. So cyclic planar, each atom sp2, and it must follow Huckel's rule, 4n+2 pi electrons. So if your free radical reactions, example is the free radical polymerization, metal-mediated reactions. An example is the sodium metal-mediated Birch reduction. So some questions as we conclude. What are the key features of a substitution? What are the key features of elimination reactions? Explain the significance of rearrangement in terms of stability, and why is it important to know these types of reactions listed in this concept development. So later on, we'll discuss different types of substitutions and different types of eliminations. But I want to remind everyone, you're not alone. We are all in this as a scientific community. Reach out to people if you need help. Get the help that you need. Strategize, plan, use the resources at your disposal. You can do it. People are rooting for you. Keep up the good work. Glad to see that you're doing well. Hope everyone's doing well. And this ends this episode of Lecture Chaos.
Avant-propos. Le temps et le hasard nous arrivent tout. Après avoir travaillé et fait du tutorat en tant qu'étudiant de premier cycle et avoir reçu une bourse complète pour les études supérieures, ce livre est un moment opportun et un exemple de le faire suivre pour que d'autres en bénéficient. En effet, si vous êtes au collège, étudiant la chimie, ce livre présente une opportunité de vous aider dans votre réussite en tant que guide complémentaire. Si vous choisissez de l'utiliser, rappelez-vous les concepts, utilisez le manuel à venir et utilisez différentes méthodes pour un renforcement positif sain. Les objectifs de la mnémotechnique incluent l'apprentissage des versions simplifiées des concepts, et non des détails techniques lourds, qui dans de nombreux cas entoureront des exceptions. Il est vrai que la répétition et la pratique aident à renforcer les concepts que vous apprenez. Tu peux le faire. DJF. Biographie des auteurs. David Ferguson. David Ferguson est un nouvel étudiant diplômé qui a récemment reçu une bourse complète pour étudier la chimie. Il a fréquenté le Georgia Institute of Technology et l'université Taylor, où il a obtenu son diplôme avec mention. Il a été inscrit sur la liste du doyen des deux institutions et a reçu de nombreuses bourses à Georgia Tech et à l'université Taylor. David Ferguson a fait des recherches avec le Dr. C.N. au Georgia Tech Research Institute ainsi qu'avec le Dr. Daniel King et le Dr. V.C. Shula à l'université Taylor. Il aspire à servir dans le milieu universitaire et à aider à enseigner et à encadrer de futurs étudiants en sciences après. De Vincent Miranda. Vincent Miranda est un étudiant senior en pré-médecine à l'université Taylor qui travaille sur un baccalauréat ès sciences en biochimie. Il a reçu le prix étudiant le plus remarquable en chimie organique, biochimie et chimie inorganique à l'université Taylor. Il a également aidé le Dr Daniel Kaluka, PhD, dans ses recherches de premier cycle sur les protéines émiques d'un parasite du paludisme, Plasmodium falciparum. Vincent est un joueur de basket-ball collégial de l'université Taylor et a obtenu une place dans l'équipe académique de tous les districts du district 2 de la NAIA en 2020. Après avoir obtenu son diplôme de premier cycle, Vincent aspire à fréquenter une école de médecine et à obtenir son doctorat en médecine. Dévouement. Ce livre est dédié aux dizaines de personnes qui m'ont aidé et inspiré. Plus précisément mes parents, mon frère, ma sœur et ses enseignants à l'université et au lycée qui m'ont rendu la science accessible. Le nouveau chimiste. Symbole tout droit réservé. Publication du nouveau chimiste 242, DJF. Section 1. Fondation. La chimie organique est un sujet qui nécessite des efforts, de la concentration et des compétences. Ces fondations ont été sélectionnées après un examen guidé et une observation des concepts qui facilitent et soutiennent une bonne compréhension à mesure qu'un étudiant progresse dans cette discipline en chimie. Ces fondements, de la fraction aux métaux, mettent en évidence une orientation conceptuelle, des idées clés, des points et des aides-mémoires pour soutenir votre succès en chimie organique. Apprendre la chimie organique, c'est comme construire une maison, cela demande du temps, des compétences et des efforts persistants. Commençons. Développement de concept 1. Introduction. Objectif. Apprenez les définitions clés. Comprendre les idées clés et la pertinence des structures de points de Lewis. Comprendre quelques concepts de mécanique quantique simplifiée. Molécules organiques. Les molécules organiques peuvent être définies comme de multiples atomes associés ou liés ensemble, constitués principalement de carbone. En bref, les molécules organiques sont des molécules à base de carbone. Figure 1.1. Cette image montre la structure de la ligne de liaison de la cyanocobalamine, autrement connue sous le nom de vitamine B12. Ces molécules peuvent ou non avoir la même formule moléculaire. Dans les cas où la formule moléculaire est la même mais la structure n'est pas la même, isomères structuraux. Quelques exemples incluent l'acétone et l'éther diméthylique. Figure 1.2. Cette image montre deux isomères structuraux, constitutionnels, l'acétone à gauche et l'éther diméthylique à droite. La constitution ou la connectivité n'est pas la même, isomère constitutionnel. Notez que les isomères mentionnés précédemment, constitutionnels, sont parfois interchangés avec le terme structurel. L'arrangement dans l'espace 3D n'est pas le même, stéréoisomère. Figure 1.3. Cette image montre une paire d'énantiomères, de gauche à droite, S-1 bromo-1-chloroéthane et R-1 bromo-1-chloro. Éthane. Sous-classe de stéréoisomères. Les isomères optiques sont des molécules qui font tourner la lumière différemment et leurs images miroirs ne sont pas superposables, autrement appelés énantiomères sont normalement désignés par E, Z, R ou S. Isomères géométriques qui sont des molécules qui ont des images miroirs non identiques, et la disposition autour du plan de la double liaison est différente, c'est-à-dire si outrant. Les molécules organiques peuvent être linéaires. La forme moléculaire linéaire est observée dans le HCN, cyanure d'hydrogène, ou l'acétylène, C2R2, ou elle peut encore être plane mais trigonale comme le formaldéhyde, qui est plan trigone. Figure 1.4. Cette figure montre les structures des lignes de liaison, de gauche à droite, du cyanure d'hydrogène, de l'acétylène et du formaldéhyde. De plus, la molécule peut avoir un arrangement 3D tel que le méthane, existant sous la forme d'une molécule tétraédrique. Figure 1.5. Cette figure montre les structures des lignes de liaison du méthane et du formaldéhyde. Explication schématique des molécules et des composés. Figure 1.6. Cette figure montre les différences et les relations entre les molécules et les composés. La structure des molécules 3D. La structure des molécules tridimensionnelles 3D peut être prédite à l'aide d'une application de structure de points de Lewis correctement dessinée, appelée théorie de la répulsion des paires d'électrons en coquille de valence, VSEPR. VSEPR implique la théorie des liaisons de valence, montrant tous les électrons de valence et incluant les électrons de liaison et non liés, dans certains cas appelés paires isolées, et maximisant la séparation dans l'espace 3D afin de minimiser les répulsions, connecté à la loi de Coulomb en ce qu'une plus grande distance minimise le potentiel distribution d'énergie pour des charges similaires. VSEPR est une alternative qui peut informer et commencer le voyage dans la compréhension de la géométrie moléculaire, qu'il s'agisse des alcynes linéaires, des arrangements planaires trigonaux des atomes de carbone dans certains alcènes ou des arrangements tétraédriques des atomes de carbone autour de certains atomes de carbone dans les alcanes. Une autre alternative consiste à utiliser la mécanique quantique qui utilise des fonctions d'onde qui sont des descriptions mathématiques des distributions de probabilité d'électrons pour produire des orbitales atomiques. Il existe certaines limites à cette méthode en ce qui concerne la précision comme avec la méthode précédente, VSEPR, compte tenu des simplifications théoriques utilisées. Globalement, l'objectif est de mieux comprendre ce qui se passe dans la nature. Par exemple, avec la mécanique quantique, nous pouvons entrer dans la théorie de l'hybridation et utiliser le mélange mathématique des fonctions d'onde pour approfondir notre compréhension de ce qui est observé dans la nature. Dans le même but, grâce aux idées de la théorie des liaisons de valence, nous pouvons prédire les angles de liaison pour le méthane. Plus précisément, l'angle de liaison intramoléculaire HH dans le méthane, des déviations sont observées et l'hybridation explique ces déviations avec des explications. Ces explications impliquent Les arrangements linéaires ont des atomes de carbone qui sont hybrides sp, un sp plus 2 pages s. Les arrangements planaires trigonaux ont des atomes de carbone hybrides sp2, un sp2 plus une page. Les arrangements tétraédriques ont des atomes de carbone qui sont hybrides sp3 et un sp3 plus 0 page. D'autres hybridations se produisent moins fréquemment, dans la chimie organique traditionnelle. Cependant, avec des géométries plus élevées communes aux composés inorganiques, il peut y avoir bipyramidal trigonal, sp3d, ou octaédrique, sp3d2. Remarque, la mécanique quantique implique également l'utilisation de la théorie des orbitales moléculaires pour comprendre d'autres interactions, mais cela sera discuté dans l'annexe. Dans le même ordre d'idées, la mécanique quantique permet également aux chimistes de s'exprimer sur les densités électroniques régionales telles que le long de l'axe internucléaire, liaison sigma, ou le long des axes perpendiculaires X, Y, Z, liaison pi. Ces idées peuvent être appliquées aux arrangements de liaisons tels que les liaisons sigma se produisant dans des liaisons simples, ainsi que des doubles liaisons possédant des liaisons sigma et une liaison pi. En outre, dans les triples liaisons, il existe une liaison sigma et deux liaisons pi. Des questions faciles. Qu'est-ce que la chimie organique et quelle en est l'origine historique? Indice, Friedrich Wöhler et 1828. Quelle est une classe de composés organiques? Quels sont les trois types d'isomères différents? Moyen. Expliquer la théorie des liaisons de valence en termes généraux simples. Quel est un exemple moléculaire, où la théorie des liaisons de valence n'explique pas avec précision ce qui se passe dans les molécules? Dur. Quelles sont l'hybridation des atomes de carbone dans l'acétonitrile? Quelles sont les désignations de sigma et pi pour les liaisons dans l'acétonitrile? Développement de concept de groupe fonctionnel et autres idées. Objectif. Comprendre ce qu'est un groupe fonctionnel. Comprendre le format clé de la nomenclature organique. Comprendre le rôle des forces intermoléculaires, FMI. Les groupes fonctionnels sont des parties caractéristiques des molécules, qui transmettent des propriétés chimiques spécifiques aux molécules qui les possèdent. Les groupes fonctionnels font de nombreuses choses mais ils nous permettent principalement de compartimenter les informations sur les molécules, les composés et les réactions. Les groupes fonctionnels nous donnent un aperçu des interactions chimiques telles que les interactions intermoléculaires, ainsi que nous donnent plus d'informations sur la compréhension des propriétés des molécules. Cela inclut les propriétés physiques, points d'ébullition et points de fusion, et les solubilités. Compte tenu de l'utilité des groupes fonctionnels, ils possèdent également une empreinte moléculaire caractéristique qui est détectée de nombreuses manières, notamment dans les spectres, qui seront discutés dans un développement de concept ultérieur. Figure 2.1. Ces molécules énumérées ci-dessus transmettent différents attributs chimiques et propriétés physiques à la molécule qui possède ces fragments. De gauche à droite, hydroxyle, sulfurhydryl et benzène. Première ligne, carboxylate, phénol, thiophène. Deuxième ligne, et furane. Dernière ligne. Type de molécules et leurs propriétés. Il existe plusieurs types de molécules dans le monde. Cependant, dans la discipline de la chimie organique, il existe des molécules spécifiques qui sont fréquemment discutées, notamment celles-ci. Alcanes. Les alcanes, autrement connus sous le nom de paraffine, sont des hydrocarbures saturés et des composés aliphatiques. Ces molécules forment une série d'homologues avec une unité répétitive méthylène, chemin 2, et avec la formule générale CnH2n+2, et se terminant par le suffixe -ane. Par exemple dans l'ordre croissant de 1 à 5. Méthane chemin 4. Éthane C2h6. Propane C3h8. Butane C4h10. Pentane C5h12. Les préfixes suivants sont ex, 6 carbone, hept, 7 carbone, octobre, 8 carbone, non, 9 carbone, et décembre, 10 carbone. Ces préfixes de met, a, dec, sont applicables tout au long de la dénomination des composés organiques, alcane, alcène, alcyne, alcool etc. Alcène. Les alcènes, autrement appelés oléfines, sont des hydrocarbures insaturés et ils sont considérés comme des composés aliphatiques. Ils contiennent au moins une double liaison, formant une série homologue avec la formule CnH2n. Ces molécules se terminent par le suffixe n. Alcyne. Les alcynes, autrement connus sous le nom d'acétylène, sont des composés insaturés ayant une triple liaison. Ces molécules forment une série homologue avec une formule générale de CnH2n2. Ces molécules se terminent par le suffixe -ine. Il existe plusieurs autres molécules qui forment une série homologue au sein de leur groupe, notamment les acides carboxyliques, CnH2n plus 1 COO, et les aldéhydes, CnH2n plus 1 CHO. Alcool. Alcool dont le groupe fonctionnel principal pour l'identification est le groupe hydroxyle, O. Il est notamment prioritaire dans la pratique de la nomenclature. Les exceptions incluent les acides carboxyliques, selon l'IUPAC. Les alcools contiennent un ou plusieurs hydroxyles formant une série homologue, CnH2n plus 1 O. Les alcools sont aliphatiques et se terminent généralement par le suffixe OL. Force intermoléculaire et autres propriétés. Avec les groupes fonctionnels viennent certaines propriétés telles que des points d'ébullition et des points de fusion spécifiques, ainsi que des températures critiques. La température autour de laquelle une vapeur ne subit pas facilement un changement de phase en liquide, et de nombreuses autres propriétés physiques. Cependant, sous la surface des propriétés physiques se trouvent les caractéristiques ou interactions chimiques connues sous le nom de forces intermoléculaires qui influencent et permettent des prédictions comparatives et des propriétés physiques. À savoir, il y a des forces clés à retenir. Force dipôle-dipôle. Ce sont des forces qui se produisent entre les molécules, intermoléculaires, avec un moment dipolaire ou une constante diélectrique significative. Ces molécules sont autrement appelées polaires. Ces forces intermoléculaires, FMI, sont relativement fortes. Une version relativement plus forte de cette force est la force intermoléculaire de la liaison H. Liaison hydrogène. La liaison hydrogène est une force plus forte, parfois appelée force dipôle-dipôle forte. C'est un FMI relativement fort, certains le considèrent comme le plus fort. Il se produit dans l'eau et d'autres molécules avec des liaisons hydrogène avec N, O ou F. Ion dipôle. Cela se produit entre les ions et les molécules polaires, par exemple, avec la solvatation des cristaux de chlorure de sodium dans l'eau. Force de dispersion de Londres. Les forces de dispersion de London se produisent dans toutes les molécules et sont basées sur les interactions coulombiennes entre les dipôles transitoires, essentiellement temporaires. Ces forces électrostatiques entraînent des interactions transitoires. Force van der Waals. Maintenant, une force plus faible qui se compose de deux types comprend la force de van der Waals qui est brièvement discutée ici et plus de détails peuvent être trouvés dans d'autres textes. Il convient de noter que les IMF et leurs forces sont basées sur des groupes fonctionnels, la structure chimique et les types de liaisons chimiques dans ces molécules. Une liaison chimique. Liaison covalente polaire. Une liaison covalente se produit entre des atomes présentant des différences d'électronégativité importantes. Plus précisément, cette liaison se produit avec des hétéroatomes, qui font référence à différents atomes non métalliques. Plusieurs fois, l'échelle de Pauling est utilisée comme référence pour les plages afin de déterminer le type d'arrangement de liaison se produisant entre les atomes. Collage. Bien que considérée comme une construction théorique dans certains cas, est considérée sur un spectre, une liaison covalente polaire existerait autour du milieu. Liaison covalente. C'est presque à une autre extrémité du spectre de liaison où il y a une différence moins significative dans l'électronégativité. Ionique. C'est à l'autre extrémité du spectre de liaison. Cela se produit entre les métaux et les non-métaux. Par exemple, dans le chlorure de sodium, il existe une grande différence d'électronégativité. Solvatation. La solvatation dépend de nombreux facteurs, y compris le principe comme se dissout comme, et des idées telles que l'hydrophilie et l'hydrophobicité. Hydrophilie et hydrophobicité. Ces termes font référence à la position des molécules par rapport à l'eau, qu'elle ait une affinité importante pour l'eau, hydrophile, épris d'eau, ou une affinité moins importante pour l'eau, hydrophobe, haïsseur d'eau. La tendance des molécules est la suivante, les composés polaires et ioniques ont tendance à être hydrophiles, par rapport aux composés covalents et non polaires qui ont tendance à être hydrophobes. Nomenclature. La nomenclature selon l'IUPAC est basée sur 4 parties. Le préfixe, cela indique normalement le numéro de chaque substituant ou attachement de groupe fonctionnel. Les préfixes incluent di, tri, tétra. Le locant, qui est le nombre qui décrit l'attachement du groupe fonctionnel ou la position des substituants. 3. La chaîne mère, c'est normalement la plus longue chaîne continue de la molécule. Le suffixe, il est basé sur le groupe fonctionnel président ou prioritaire, la chaîne ou l'arrangement de liaison, c'est-à-dire simple, double ou triple. Les suffixes sont généralement classiques en se terminant par an, alcane, en, alcène, in, alcine, aminamine, amide, amide, ouac, acide carboxylique, at, esté, ou acétone. Fait important à noter, le groupe fonctionnel de l'alcool, l'hydroxyle, O, est normalement prioritaire dans l'ensemble. Les substituants sont transcrits ou décrits dans le nom en fonction de l'ordre alphabétique relatif, donc éthyle avant méthyle et ce schéma se poursuit. Idée globale clé, préfixe locant parenchin suffixe, généralement. Toute autre élaboration sera discutée plus loin dans le texte. Des questions. Facile. Qu'est-ce qu'un groupe fonctionnel et citer plusieurs exemples de groupes fonctionnels? Indice. O. Quels sont les 3 types de molécules organiques? Qu'est-ce qu'une force intermoléculaire? Moyen. Expliquer les forces dipôle-dipôle. Quel est un exemple moléculaire, où les forces intermoléculaires expliquent une propriété physique telle que le point d'ébullition? Dur. Quelle est la différence entre la liaison hydrogène et les forces de dispersion de Londres? Expliquer le processus global de dénomination des composés organiques simples? Du concept 3. Structure, conformation et projection. Objectif. Comprendre et être capable de dessiner des structures de points d'électrons de Lewis, des structures condensées et des structures de lignes de liaison. Comprendre et être capable de dessiner différentes conformations, principalement celles du cyclohexane. Comprendre et être capable de dessiner et d'identifier les projections de Fischer et les projections de Newman. Ouvrage. Les structures sont des représentations schématiques de différentes molécules et elles fournissent un moyen de comprendre ce qui se passe dans la nature. Il existe une variété de structures différentes utilisées en chimie. Les principaux exemples dans la discussion suivante seront les structures de points d'électrons de Lewis, les structures condensées et les structures de lignes de liaison. Structure de points d'électrons de Lewis. Les structures de points de Lewis sont construites sur certaines idées clés telles que la valence de l'atome et la règle de l'octet. Il existe également des exceptions spécifiques pour la période 3 et au-delà. Valence. La valence fait référence à la quantité d'électrons qu'un atome perdra, souvent résultant en un ion chargé positivement, un cation, un gain, souvent résultant en un ion chargé négativement, un anion, ou une part, généralement dans les molécules covalentes, afin d'avoir une configuration stable d'électrons de gaz rares. La valence peut être déterminée à l'aide du tableau périodique. Le numéro de groupe, numéro de colonne verticale, dans le tableau périodique est désigné par la valence. Cette valence correspond normalement à la charge ou au nombre d'oxydation, et son signe ultérieur dépend du type d'atome, de sa réactivité et de ce avec quoi il réagit. Un point clé à noter. La valence peut être montrée rapidement à l'aide des structures de points de Lewis et l'arrangement orbital peut être expliqué simplement, mais pas avec une précision complète, à l'aide du modèle de Bohr. Le modèle de Bohr consiste à utiliser le symbole atomique entouré de cercles représentant l'orbite de l'électron avec des points symbolisant les électrons. Le modèle de Bohr coïncide à certains égards avec la configuration électronique de l'atome. Règle de l'octet. La règle de l'octet est un principe qui trouve des applications dans la théorie des résonances, les mécanismes chimiques simples et les réactions. La règle de l'octet est basée sur l'idée que les atomes gagnent, partagent ou perdent des électrons afin d'avoir un octet complet, 8 électrons extérieurs. Il existe des exceptions, par exemple certains atomes peuvent perdre des électrons pour posséder la configuration électronique de l'hélium, 2 électrons externes. Cependant, pour la plupart des atomes des périodes 1 et 2 du tableau périodique des éléments, ces éléments obéissent généralement à la règle de l'octet. Cette règle est utile pour prédire la réactivité et expliquer simplement la justification de certaines réactions chimiques. Exception spécifique pour la période 3 et suivante. En fonction de l'atome, de sa réactivité et de ce avec quoi il réagit, il existe des exceptions à la règle de l'octet. Par exemple avec certains atomes métalliques tels que l'aluminium, Al, et d'autres, y compris le fer, des non-métaux tels que le phosphore et le sélénium, et des gaz nobles tels que le xénon. Il existe de nombreuses exceptions, mais la règle fournit toujours un cadre pour le développement conceptuel. Méthode d'écriture de structure de points d'électrons de Lewis. Pour les atomes ions. Pour les atomes et les ions, considérez principalement le numéro de groupe et la configuration électronique. Par exemple, la structure des points d'électrons de Lewis du chlore ou de l'hydrogène. Figure 3.1 à la figure ci-dessus montre les structures de points d'électrons de Lewis d'un atome de chlore et d'un atome d'hydrogène, de gauche à droite, respectivement. Pour les molécules, à commencer par déterminer le nombre total d'électrons parmi les atomes de la molécule. Ensuite, dessiner des liaisons simples entre chaque atome. Soustraire 2 électrons, pour chaque liaison simple, de l'électron total. Compter. Ajouter des liaisons supplémentaires si nécessaire, par exemple pour les liaisons carbone-oxygène dans les aldéhydes et les cétones. La disposition des liaisons se présente généralement sous la forme d'une double liaison. Connaissez et observez les tendances. Une fois que toutes les liaisons supplémentaires nécessaires ont été notées, soustrayez la quantité correcte d'électrons pour les liaisons supplémentaires ajoutées. Typiquement, les électrons restants les désignent comme des paires isolées, autour des atomes concernés. Structure condensée. Les structures condensées sont importantes dans le processus de compréhension de ce que les structures de lignes de liaison représentent et montrent. Dans les structures condensées, tous les hydrogènes sont représentés attachés au carbone par exemple. Figure 3.1b, la figure ci-dessus montre la structure condensée du S-2-bromobutane. Structure de la ligne obligataire. Les structures en ligne de liaison sont la prochaine étape après les structures condensées. Celle-ci ne montre que le cadre carboné avec chaque carbone représenté par une courbure de la chaîne et l'hydrogène non noté, mais déduit ou supposé, jusqu'au point où un octet complet autour de l'atome de carbone. Cela signifie que les hydrogènes ne sont pas représentés mais implicites au point que la valence du carbone est satisfaite. Par exemple, égale. Figure 3.2 Les structures ci-dessus montrent la structure de la ligne de liaison du butane, sous laquelle se trouve la structure condensée du butane. Les structures de ligne de liaison sont utiles et efficaces. Note. Lors de la découverte de la structure du benzène, cyclohexatriène ou cyclohexatrie 1,3, 5N, Auguste Koekul a déterminé la structure d'une molécule à cycle à 6 carbone avec des liaisons simples et doubles alternées. Cette structure, vue ci-dessous, est un bon point de ramification des structures condensées aux structures égale. Figure 3.3. La figure ci-dessus montre, de gauche à droite, une version de la structure de coccule du benzène et la structure de la ligne de liaison du benzène. Conformation. Les conformations sont des molécules qui ne diffèrent que par des rotations autour de liaisons simples, autrement qualifiées de liaisons sigma. Ces rotations alternées affectent les énergies potentielles des molécules en les augmentant, comme on le voit dans la conformation éclipsée, ou en les diminuant, comme on le voit dans L anticonformation. Les énergies potentielles des conformations sont attribuées à la déformation annulaire qui est basée sur la déformation angulaire et la déformation de torsion. La déformation angulaire est causée par les angles de liaison alternés qui ont dévié des angles de liaison idéalisés suggérés dans VSEPR. La contrainte de torsion est causée par la répulsion due aux forces de dispersion, une force intermoléculaire, et cela peut provoquer des encombrements stériques. Les conformations peuvent être décrites expérimentalement à l'aide d'un graphique de l'angle dièdre en fonction de l'énergie potentielle. En règle générale, le cyclohexane est tracé montrant l'énergie potentielle des différentes conformations en énergie potentielle croissante, la conformation de la chaise, insérer l'image, ayant l'énergie potentielle la plus faible, puis le bateau de torsion, insérer l'image, suivi de la conformation du bateau, insérer l'image, et enfin la demi-chaise, insérer l'image, à l'énergie potentielle relativement la plus élevée parmi les conformations de cyclohexane. Chaise. Twist bateau. Conformation bateau demi-chaise. Figure 3.4a. Les structures des lignes de liaison des différentes conformations du cyclohexane. Figure 3.4b. La figure ci-dessus, utilisant des approximations relatives de l'énergie potentielle, montre la stabilité des différentes conformations du cyclohexane, à savoir, par ordre croissant de stabilité, chaise, twist boa, bateau, demi-chaise. Projection. En chimie, il existe de nombreux types de projections, cependant, deux que l'on rencontre fréquemment sont la projection de Newman et la projection de Fischer. Les projections de Newman sont des structures d'un point de vue spécifique. Nous examinons une liaison simple spécifique entre les atomes et dessinons les autres attachements par rapport à ces deux atomes. Par exemple, le butane est dessiné. Visualisez un œil regardant vers le bas C2C3 du butane afin de dessiner la projection de Newman. Figure 3.5. La figure ci-dessus montre un œil regardant vers le bas la partie de la ligne de liaison avec les carbones 2 et 3 dans le butane, afin de dessiner la projection de Newman. Figure 3.6. La figure ci-dessus montre une simple projection de Newman du butane. Les projections de Fischer impliquent une autre représentation d'un point de vue différent. La molécule est dessinée de haut en bas, normalement avec le carbone anomérique à une extrémité désignée. Généralement, les pièces jointes du groupe fonctionnel sont sur les côtés qui sont considérés comme des coins, qui sont hors du plan de le papier, et le haut et le bas de la projection sont vus comme des groupes de pointillés, qui sont dans le plan du papier. Une autre désignation de liaison utilisée est la ligne sinueuse qui représente une seule liaison à l'extérieur et derrière le plan du papier. Cette projection est généralement utilisée avec des glucides, en particulier des glucides simples. Figure 3.7. La figure ci-dessus montre l'atome d'hydrogène sur la liaison en pointillé et l'atome de brome sur la liaison en coin dans la molécule R1-bromo-1-chloroéthane. La ligne ondulée est représentée dans la molécule de thalidomide à droite du papier. Des questions. Facile. Quelle est la structure des points électroniques de Lewis de l'oxygène? Indice. Il a 6 électrons de valence. Quelles sont les idées clés pour dessiner des structures de points d'électrons de Lewis? Expliquer le concept de valence. Moyen. Expliquer la règle de l'octet. Quelle est une exception à la règle de l'octet? Dur. Dessiner la structure de la ligne de liaison pour l'anthracène. Expliquer l'ordre global de stabilité des conformations du cyclohexane. Astuce, nécessite des recherches utiles, éventuellement en groupe. Développement de concept 4. Chiralité et isomérisme. Objectif. Apprendre les définitions de mots-clés tels que isomère, chiro et conformère, comprendre les concepts de stéréoisomérie et de chiralité, comprendre la règle de Lebel-Van't Hoff. Isomère. Les isomères, tels que définis précédemment, sont des molécules ayant la même formule moléculaire mais différentes dans leur arrangement structurel, leur espace, leur connectivité ou leur géométrie autour d'un arrangement de liaison. Toutes ces différences susmentionnées définissent une sous-classe d'isomères, qu'elles soient structurelles, isomères structuraux, disposition dans l'espace, stéréoisomères, ou connectivité, isomères constitutionnels. Chaque sous-classe a sa propre signification, mais dans ce développement de concepts, les élaborations porteront principalement sur les stéréoisomères. Stéréoisomères. Les stéréoisomères, ou isomères spatiaux, sont des molécules ayant la même formule moléculaire mais des arrangements spatiaux tridimensionnels différents. Un stéréoisomère a un centre stéréogène qui est un emplacement dans la molécule où elle échange de deux groupes dans l'espace entraîne la formation de nouveaux stéréoisomères. Un sous-groupe de centre stéréogène est un centre chiral, qui fait généralement référence à un centre stéréogène avec une hybridation sp3 ou une géométrie tétraédrique. Chaque centre chiral est un centre stéréogène, mais tous les centres stéréogènes ne sont pas des centres chiraux. Les stéréoisomères peuvent être divisés en trois autres catégories, les énantiomères, les diastéréoisomères et les hétéroisomères. Énantiomères. Les énantiomères sont des isomères optiques. Ces isomères optiques sont des molécules qui sont des images miroirs non superposables les unes des autres. Les énantiomères ont généralement des centres chiraux. Les énantiomères sont très importants dans l'industrie pharmaceutique avec des énantiomères spécifiques dans les médicaments, ayant des effets spécifiques. Cela se voit avec les exemples classiques de la thalidomide, de l'ibuprofène et du darvon, où la stéréospécificité joue un rôle important dans la détermination du potentiel thérapeutique et des effets thérapeutiques. Figure 4.1. La figure ci-dessus montre, de gauche à droite, les structures en ligne de liaison des molécules, thalidomide, ibuprofène et darvon. Les énantiomères sont généralement désignés par les signes de configuration absolue qui sont R, rectu, et S, sinisté. Figure 4.2. La figure ci-dessus montre, à partir de gauche à droite, l'orientation associée aux différentes configurations absolues. Les mélanges des deux énantiomères sont appelés racémiques, généralement ce sont des mélanges de proportions égales. Le processus de formation des deux énantiomères en tant que produit est connu sous le nom de racémisation. Le produit du procédé mentionné ci-dessus est connu sous le nom de racémate. Ces molécules sont aussi désignées par la configuration relative qui sont dextrogir, D+, ou lévogir, L. Les termes dextrogir et lévogir font référence à la rotation optique, ou à la façon dont les molécules font tourner la lumière, qui est la rotation gauche, lévogir, ou la rotation droite de la lumière, dextrogir. Mettre en image le polariseur. De plus, la mesure dans laquelle la lumière est tournée est normalement indiquée à l'aide d'une rotation spécifique. Il existe d'autres applications avec la dispersion optique, la polarimétrie, le dichroïsme circulaire et d'autres phénomènes de polarité. Attribuer des configurations. Configuration relative. Dextrogir, ou lévogir, doivent être attribués expérimentalement généralement par l'application appropriée d'un dispositif optique tel qu'un polarimètre. pour observer et mesurer comment la molécule fait tourner la lumière et dans quelle mesure ou degré elle la fait tourner. Configurations absolues. Des configurations absolues peuvent être attribuées à l'aide d'un système d'étiquetage numérique prioritaire appelé règle de priorité de Kahn-Engel-Prelot. Ces règles donnent la priorité en fonction de la masse atomique. Les atomes plus gros ont la priorité la plus élevée, 1, et les atomes les plus petits ou les moins lourds ont la moindre priorité, généralement l'hydrogène dans de nombreuses molécules. Par exemple un bromo, un chloropropane, la priorité est notée. Le brome est prioritaire 1. Le chlore suit avec la priorité 2. L'éthane est prioritaire 3. L'hydrogène est prioritaire 4. Comme on le voit ci-dessous, il s'agit donc de S1 bromo, un chloropropane. Figure 4.3. La figure ci-dessus montre l'image de la structure de la ligne de liaison du S1 bromo, un chloropropane. Diastéréoisomère. Il s'agit d'une sous-classe d'isomères optiques également appelés isomères géométriques. Les diastéréoisomères sont des isomères avec la même formule moléculaire mais des arrangements différents dans l'espace qui se traduisent par des images miroirs non identiques. Ceux-ci peuvent généralement être identifiés en attribuant d'abord la configuration absolue des centres stéréogéniques puis en comparant les images miroirs pour déterminer si elles sont identiques ou non. Ces étapes répertoriées précédemment sont dans un ordre suggéré. Les sous-classes de diastéréoisomères sont les isomères citrans et les conformères, qui peuvent être divisés en rotamères. EZ et isomérie citran. Comme dextrogir et lévogir est une affectation relative pour la stéréochimie, il en va de même pour si et tran. L'isomérie si et tran permet de désigner les arrangements spatiaux basés sur des groupes similaires, par exemple tran-1,2 dichloroéthène ou 6,1,2 dichloroéthène. Ce système relatif, si ou tran, peut devenir obscur très rapidement, donc pour fournir un système plus méticuleux, les règles de priorité de Kahn-Engel-Prelot sont utilisées pour étiqueter les substituants sur le double liaison en utilisant le EZ, integeant ou opposite, Z usamment ou samside. Ce système susmentionné offre plus de clarté. Comme dextrogir et lévogir est une affectation relative pour la stéréochimie, il en va de même pour si et tran. L'isomérie si et tran permet de désigner les arrangements spatiaux basés sur des groupes similaires, par exemple tran-1,2 dichloroéthène ou 6,1,2 dichloroéthène. Ce système relatif, si ou tran, peut devenir obscur très rapidement, donc pour fournir un système plus méticuleux, les règles de priorité de Kahn-Engel-Prelot sont utilisées pour étiqueter les substituants sur le double liaison en utilisant le EZ, integeant ou opposite, Z usamment ou samside. Ce système susmentionné offre plus de clarté. Comme indiqué précédemment, les règles de priorité de Kahn-Engel-Prelot donnent la priorité la plus élevée, 1, au plus grand substituant ou au substituant avec la plus grande masse atomique. Et les substituants suivants sont étiquetés avec les nombres, 2,3, 4, basés sur les masses atomiques. Conformateur et rotamé. Un conformère est un arrangement ou une conformation d'une molécule basée sur la rotation de liaison simple, qui a entraîné un minimum d'énergie potentielle. Un exemple classique de conformateur est le cyclohexane dans lequel vous avez différents conformères représentés dans le graphique ci-dessous. Figure 3.4b. La figure ci-dessus, utilisant des approximations relatives de l'énergie potentielle, montre la stabilité des différentes conformations du cyclohexane, à savoir, par ordre croissant de stabilité, chaise, twist boa, bateau, demi-chaise. Un rotamère n'est qu'une conformation d'une molécule qui résulte d'une autre rotation des liaisons simples de la molécule. Anomère. Un isomère formé en raison d'une variation géométrique trouvée au niveau de certains atomes dans des molécules spécifiques. Les anomères sont généralement observés et décrits dans les glucides où la désignation ou est utilisée. Figure 4.4. La figure ci-dessus montre deux anomères différents, et, du déglucopyranose. Épimère. Un épimère, que l'on trouve normalement dans les paires de diastéréoisomères, est un stéréoisomère dont la configuration diffère en tout point de la molécule où la modification de la position des deux substituants entraîne la formation d'un nouveau stéréoisomère. Fondamentalement, un épimère est un isomère dont la configuration diffère à n'importe quel centre stéréogénique. Figure 4.5. La figure ci-dessus montre les épimères, en l'occurrence les énantiomères R et S, du 2-chlorobutane. Règle de Lebel-Van't Hoff. S'il y a n centres stéréogènes, avec 4 substituants différents attachés, il y a 2 n stéréoisomères différents possibles. Des questions. Facile. Qu'est-ce qu'un isomère? Indice. Même formule moléculaire mais, quels sont les différents types d'isomères? Expliquez le concept d'énantiomère. 4. Qu'est-ce qu'un racémate? Moyen. Expliquez ce qu'est un diastéréoisomère. Quelles sont les deux sous-classes de diastéréoisomères? Dur. Expliquez les règles de priorité quand un bol prelo pour désigner la configuration absolue. Développement de concept 5. NUC éléophilicité et électrophilicité. Objectif. Apprenez les définitions de la nucléophilie et de l'électrophilie. Comprendre les tendances avec nucléophilie et basicité ou électrophilie et acidité. Comprendre les différences avec nucléophilie et basicité ou électrophilie et acidité. Nucléophilie.
Thanks for listening. We're glad you were able to tune into this podcast. Once again, this is The New Chemist, where we discuss chemistry, which simply put is the science of change, as well as the other sciences, careers, community, research, and COVID-19. Thanks again for listening. Note, the views on this podcast represent those of my guests and I.